Hey everyone, welcome back to my channel AI Connect Grow. In our last video, we introduced you to transformers and discussed their key components. The link to that video is in the description below. Now let's dive into the PyTorch implementation of input embedding and positional encoding. I'm using PyTorch in order to implement input embedding and positional encoding in transformers. PyTorch is one of the most popular and powerful framework for building and deploying AI models. If you're new to PyTorch, don't need to worry. I'll be explaining how to implement input embedding and positional encoding using PyTorch in a very simple way. Make sure you write the code while following the video. This will make your understanding more clear and a better coder. You can know more about PyTorch here in pytorch.org and understand how to install PyTorch and go through their documentation. Let's begin. I'm making use of Visual Studio Code as the IDE. You can make use of PyCharm or IntelliJ or Visual Studio Code or Jupyter Notebook in order to implement this code. Before we even start implementing it, we need to make sure that these modules are installed. In order to do that, you can go ahead and install them by making use of the command pip install torch. This is how you'll be installing your PyTorch modules. Since I've already installed it, it shows me that requirement already satisfied. The next thing for you to install is NumPy package. You can just do it by making use of pip install NumPy command. It also says that requirement already satisfied. I'm just reiterating once again that even if you're new to Python, even if you're new to PyTorch, please follow this video. You will easily be able to implement input embedding without having prior experience of PyTorch or Python, because these commands are very simple and easy to follow. Now that we have installed PyTorch package by making use of command pip install torch, the first thing to do is to import PyTorch and NumPy libraries. NumPy is basically used for working with arrays. Let me run the code first so that I can explain you each line of code along with the output displayed. So let's just go ahead and run the file. Let us understand the main function. Here we have defined the parameters such as vocabulary size, which we have initialized as 10,000, embedding dimension, which we have initialized as 6, sequence length as 4, batch size as 2. As we have seen in the image over here, wherein we took two sentences, tokenized them and indexed them, and then send the batch of input sequences to embedding layer, we'll be doing the same thing here in the code as well. Here we have taken two sentences, I do love programming and transformers are very powerful. We are tokenizing these sentences into words by making use of simple command in Python called as .split, wherein we are splitting this sentence based on the space character over here. So as an output from this particular line, what we get is, this is the input, which is I do love programming, transformers are very powerful. And the output of the tokenization, wherein we are splitting based on the space here between the words, the word tokens are I do love programming, each different words, transformers as one word, are as one word, very as one word, and powerful as one word. Now from the input text, we have got the word tokens. Once we have the word tokens, the next step is to get the index for each of these tokens. Since this is just a sample exercise, we're just making use of random integers from torch to get the word indices randomly for the metrics of size, batch size into sequence length, which is 2 by 4 here in our example. Whereas in real time, as we discussed over here, we give the indexes based on the word frequency. Each of these tokens over here are indexed, and the shape of our metric is 2 by 4 because we have two samples and in each of the sample we have 4 words. This is being sent as input to input embedding layer. We already have seen that in the input embedding layer, it learns an embedding matrix of shape, vocabulary size by embedding dimension. Here in this example, we have chosen the vocabulary size as 10,000 and embedding dimension as 4. So we'll be learning the matrix of size 10,000 by 4. Now let's understand this input embedding class. Here in this class, we are calling the base neural network module so that we can build an embedding layer. And then we are defining an embedding layer by making use of neural network embedding module and passing in the parameters such as vocabulary size and embedding dimension. You can see more parameters of PyTorch embedding here in their documentation. Now that we have defined the neural network embedding layer and its parameters, the next step is to pass the batch of input sequences to the embedding layer and then return the output from the embedding layer. This is how the input embedding class is defined. We are calling the input embedding class and passing the parameters vocabulary size, which is 10,000, and embedding dimension, which is 6-dimensional vector. Once the object is created, we are then passing the batch of input sequences to the embedding layer. This is of shape batch size into sequence length. Here in the output we can see that the input is of shape 2 by 4, which is 2 samples and 4 words in the sequence. And the embedding output is of shape 2 by 4 by 6, 2 samples, 4 words in the sequence, and 6 is the embedding dimension vector. And finally we are displaying the output embeddings and we can see the result over here. For each of the word in the sequence, it is giving a 6-dimensional vector. Since we have total of 8 words in 2 sentences, in the first sentence we had 4 words and it gives the 6-dimensional vector for each of the 4 words, and in the second sentence we had 4 words and it gives the 6-dimensional vector for each of the 4 words in the second sentence. This is the embedding vector output, which is of shape 2 by 4 by 6. Currently it is randomly initialized, but as and when we tune our model and the back propagation happens, these weights gets updated and learns the semantic relationship between the words for the data you're processing. This is how the input embedding layer works. Now let's move on to positional encoding. This is a formula that we need to implement. At first we are initializing a 0 matrix of shape, sequence length and embedding dimension. And then we are creating the position as mentioned here in the formula. We are just making use of indices from 0 to the sequence length as the position indices, which ranges from 0, 1, 2, 3 in our example. Since it creates a row vector, we are just converting it to a column vector by making use of unsqueeze, which is used to add a dimension of size 1 at a specified position in a tensor. This generates a tensor of shape sequence length, 1, where each row represents the position index in the sequence, ranging from 0 to sequence length -1. Now position is assigned with a column vector which is having values 0, 1, 2, 3. Next we are going to define the division term. As given in the formula, we are going to implement this in PyTorch. This particular line over here computes the scaling factors for each dimension. Torch.arrange 0 generates a sequence of integers from 0 to embedding dimension, jumping at 2 levels, representing indices for even dimensions. Math.log divided by embedding dimension. This ensures the scaling factors decrease exponentially as the dimension index increases. Finally, torch.exponent applies the exponential function to compute the actual scaling factors. The resulting tensor has a shape embedding dimension by 2 and is used to control the frequency of the sine and cosine functions. Now that we have the position and division term, for the even indices we are making use of sine function, and for the odd indices we are making use of cosine function. Once we have created this position encodings, we are registering it as a buffer with the name posenc and reshaping the tensor to 1, sequence length, embedding dimension. This makes it compatible for batch processing during the forward pass. Finally, we define the forward pass wherein we pass in the input embeddings and append it with the positional encodings. Inputs.size over here selects the positional encoding corresponding to the input sequence length. This addition of position encodings with the input embedding leverages positional information alongside the input embeddings. Now that we have this position encoding module created, as soon as we get the output embedding dimensions from the embedding layer, we are creating the positional encoding object by passing in the sequence length and embedding dimension. Once we have the positional encode object, and then pass embeddings to this object, which gives us the positional encoding. Let's see the positional encoding shape and the positional encoding values. Positional encoding shape is also 2 by 4 by 6, which is same as the input embedding shape 2 by 4 by 6, which we discussed earlier. And these are the values that are created as the positional encoding values, which adds the position information to the input embedding. This is how position encoding can be implemented very easily in using PyTorch code. Thank you so much. Have a nice day. Please do subscribe and support me so that I can create even more better videos for you and help you in your AI journey.